Now that we finished our unit on motion, it's time to look at what causes that motion to begin with. So back in 350 BC, or around that time, a philosopher in Greece named Aristotle had ideas about motion and how things moved. And he attempted to understand motion by classifying it either as a natural motion, and that included things like apples falling out of trees, magnets that were attracted to each other. Nothing seemed to be touching those things. The forces were acting at a distance. So that was a natural motion. It happened without anyone touching it. Or he classified it as violent motion. And we're not talking violent like a wrestling match or a gunshot. We're talking just there was some kind of contact there that's causing the motion to happen. So a couple of things that he stated when he was looking at motion, he says that the earth remains at rest, which now we know that to not be true. But at the time, think about ancient Greece, all you had to compare your motion to was the movement of the sun and the stars overhead. So it made sense why they thought this. We know it's not true now, but we know why they thought that. The other idea that we kind of talked about when we talked about projectile motion is that large objects tended to strive harder. So the more massive something was, the more it tried to fall quickly down to the ground. And your lighter objects did not strive as hard, which is why feathers would fall slowly while bowling balls would fall quickly, right? Now, again, we know that that's not necessarily true because of air resistance. The feather is under the influence of air resistance while the bowling ball is able to counteract that air resistance. But we understand why, given the limited knowledge that they had 300 years BC, why he thought these ideas. Now, those ideas stuck. You can see the time change here. From 300 BC to 1600, nearly 2,000 years, Aristotle's ideas on motion held on until the 1600s with a guy named Galileo. Now, again, we talked about the story of Galileo dropping the objects from the Leaning Tower of Pisa. We watched the video of them dropping the water bottles there, and we know that he found that all objects fall at the same rate if you account for their air resistance. So we went 2,000 years of thinking the Aristotelian ideas. Now Galileo suddenly changes that and turns it on his head. Now, from the 1600s to if Isaac Newton was born in 1642, so like the early 1700s, less than 100 years later, we have Isaac Newton entering the scene. Now, Isaac Newton was an English person. He went to University of Cambridge in England. He was a professor there, and he came up with all kinds of ideas on many different subjects. He was an astronomer, a philosopher. He studied a little bit of religion and alchemy, which is very early chemistry. And he, in part of his studies, was able to solve 3 mysteries that had plagued us for years. You saw the 2,000 years between Aristotle and Galileo. Suddenly, Isaac Newton's on the scene and everything's solved, right? So we've got the laws of motion, which is what we're going to talk about. The laws of planetary orbits, so how planets revolve around the sun. They're not perfect circles, they're actually more oval-shaped. And in order to solve those oval-shaped orbits, he ended up creating or pulling together the ideas of calculus. So you have him to thank for that. So he came up with these ideas of forces, that motion is caused by some kind of force. Now, force, very simple definition, is a push or a pull. So very simple definition, a force is just a push or a pull. And we can measure that amount of push in a unit called the Newton. So imagine how it got that name. So we can characterize or categorize forces based on the type of forces that we have. We have contact forces, which is where there's physical contact being made. So in the picture down below, you see the baseball bat hitting the baseball. That's a contact force. And then there's also field forces. So gravity, the earth is not touching objects, pulling it down. That's a field force. There's a gravitational field around objects that pulls them towards the center. Or magnetic attraction. Now, funny thing is, this sounds a lot like natural motion and violent motion, doesn't it? We're just kind of putting a little bit more reason behind what's going on. But it turns out Aristotle was not dumb. He just wasn't quite as advanced in his scientific knowledge. So contact forces, they're actually touching. Field forces, they're acting at a distance. Now there's actually a lot of different types of forces. So feel free to pause the video and write a little table of the different forces, and I'll come back and explain these. 1 second. Okay, so now that you've written them down, let's talk a little bit. So friction is a force. It's an opposition forces between two objects that are sliding past each other. So when we talk about direction of friction, it's always going to be acting opposite to where we're trying to go. If you're trying to push a block this way, the force, or the force of friction, is opposing that motion. Now, it's opposing, so you'll never have more friction than you have force pushing it. It's not like we're standing here and then suddenly the friction gets really high and we start moving backwards. That doesn't happen. So friction is only enough to oppose the motion that's happening, or it's less than that. If it's less, then of course we can move. Normal force is a supporting force, and by normal we don't mean not weird normal. We mean normal as in perpendicular to. So if you're doing construction work and you have to put the angle at a normal, or the beams, the poles at a normal, that means that you want to put them perpendicular to the surface that you're working with. So that's a contact force between the surface and the object that's sitting on the surface. Okay, so normally it's going to be equal and opposite to your gravitational force, the gravity that's pulling you down, but as your surface changes, so does that normal force. So it's not always going to be equal and opposite to gravity. It depends on the angle of that surface. It's always going to be perpendicular to the surface itself. And then spring force, think like a spring or a rubber band, that force that's trying to get it back the way it wants to go. You pull a spring apart, but then as soon as you let go, boom, it goes right back the way it wants to. So that force is trying to act opposite to the way that you pull it. You pull the spring out, it's wanting to go back in the way that it's used to going. Okay, 3 more. You ready? Write these 3 down and then we'll talk. Okay, so tension is the kind of like spring force, except you don't have deformation. So like a rope or a string, that pull on a rope, a string, a cable is tension, the force of tension. And the direction of tension force is always going to be away from the object and with the string, rope, cable, whatever. Thrust force is what makes a rocket go. It's what pushes forward a boat in the water. That is the force that is counteracted. So movement's going this way, thrust force is going that way. It's the hot gases escaping from the rocket or from the jet engine. It's the tires pushing against the road to thrust forward the car going down the highway, and it's what makes things go. Even between your shoes and the pavement, there's a thrust force pushing you forward as your shoes push against the ground. And then finally, weight force. Weight force is the force of gravitational attraction on a mass, and that's going to be towards the center of the earth. It's always going to push down towards the center of the earth. So let's talk very briefly about Newton's first law, and then Monday we'll cover the second and third. But the first law is called the law of inertia. Now, inertia, I tend to think about like laziness. Things want to keep doing whatever they're doing. They don't want to change that until we force them to change. Get it? Force them to change. So the way that this is stated is an object remains at rest or moves in a straight line at a constant speed unless acted upon by a force. So it's going to do whatever it's been doing. If it's been at rest, it's going to stay at rest. If you leave the soccer ball on the field and go to lunch, you come back, as long as nobody picked it up, it's still going to be sitting there. Nothing forced it to move until somebody comes along and makes it move. Things will stay there. These desks in the classroom, we come back on Monday, they're still going to be there because nothing has made them move. But the other part of that is things are going to keep doing what they're doing until they are forced to stop. So if you throw a ball, we talked about how the horizontal velocity of a projectile stays the same. If nothing's acting on that ball to make it stop, it's going to keep going. Now with our projectile, something was acting on the ball to make it stop. That was gravity. Or the force we talked about in our table, friction. So this was a hard one to swallow for a lot of people because they're like, look, you roll a ball across the floor, it's going to stop. Yes, but it stops because there's a force acting on it, a force of friction, air resistance, gravity pulling it down, whatever the case may be. If you go up into outer space and launch something like they do satellites, they send them out, give them a velocity in a certain direction, and unless it hits an asteroid, it just keeps going. They don't have to constantly use rocket fuel to keep it going. So things will keep doing what they're doing unless some kind of unbalanced force acts on it, okay? It takes force to change the motion of an object, to make it speed up, slow down, change direction, whatever it may be. So what does that mean for us? There we go. Why do we wear our seatbelt? We wear our seatbelt because when we are in a car and we're going with the car, we're an object in motion, and we want to stay in motion until something makes us stop. Now, in the picture below, what's making the car stop is a brick wall, but nothing's making the person stop. That's why we need the seatbelt, because the seatbelt ties us to that car and causes us to stop before something else does, like the brick wall that he amazingly jumps right over. So our last little thing today is I'm going to show you a video, and this is kind of old school. She's got the shoulder pads and everything. It's a little old school, but it does a great job of showing you a trick, which isn't magic, it's actually science, but it's something that you can actually try at home and make it work using inertia. So it's a little magic trick you can try on your friends using one of Newton's laws. Okay, we'll talk about the second and third next time we're together.